So we're here today to honor the legacy of Julian C. Smith, a former director of the department, 50-year member of the faculty here in chemical and biomolecular engineering. And the lecture series is a two-part series with a first lecture that is more technical in character and a second lecture that is more for the broader public. And so here in the auditorium, I'd like to give you a little bit more background on the 2018 J.C. Smith lecturer, Professor Lynn Liu. So Professor Liu is the Theodora and William Walton Professor of Engineering at Princeton. And as I said in my introduction to the lecture series, I see her as being definitive of what modern chemical engineering can be. And I'll try to give you a little sense of that, my perspective, before she, I think, proves it to you. So I say that because she takes on hard technology problems with attention to both the product and how you might make it. And she does this by starting with fundamentals. And I think the fundamentals, and you'll see one of the strong bases in fundamentals is a polymer science, polymer physics background. But she also looks at the chemistry, looks at the thermodynamics, looks at the kinetics, and in some cases, even the continuum mechanics. And then I think more impressively, and I think importantly, something we all as engineers need to keep an eye on, she doesn't let that rigor ruin her creativity. She's also an innovator. And so she's doing all of this in a very competitive, fast-moving field of non-conventional electronics, leading one of the leading experimental groups in the world. And so these are organic electronics, small molecule, conductive polymers and semiconductor polymers, and hybrid organic and inorganic material systems for a whole variety of electronic purposes, from transistors through to solar cells and others. And these are now, and through her career and her efforts and the community's efforts, are now appearing in our world. And so she told me this morning they're in the iPhone 10. Your screen on an iPhone 10 is an organic electronic LED. But her work is also getting into point-of-care devices through companies like Abbott. So again, she's really in this world, which I'm going to be a little nasty, but is filled with a lot of material science who are kind of shake and bake. She really distinguishes herself by sticking to mechanism. In a fast-moving field, I think that's critical, because that's where you get timeless value when the timely topics may only last for a few years. So, not surprisingly, she's been broadly recognized for her contributions in this field. Early on in her career, she was recognized with an MIT Technology Review Innovator Award. She won the extremely competitive prestigious Colburn Award from the AICHE for early productivity and contributions, and the Career Award from the National Science Foundation. More recently, she won the John H. Dillon Award from the American Physical Society, the highest honor for a young scientist in polymer science, and was named a global leader by the World Economic Forum, which is otherwise known as Davos. So that's truly a global recognition. She's also recently been named Fellow of the American Physical Society, and she's done all this while growing as not just a scholar and an educator, but as a leader, and in 2016 became the director of the Annealing Center for Energy and Environment at Princeton, which, as I understand it, is like the scale of our Atkinson Center, but in fact with an academic unit character that means that she's essentially running a department alongside. So we'll hear more tomorrow. We'll get a Paulette's perspective tomorrow on this career. But right now, please join me in welcoming Professor Lynn Liu for the first lecture.
Well, good afternoon, and thank you, Abe, for that very kind and I was going to close the door so that it doesn't distract me. No, I'm just keeping the latecomers at bay. For that very kind and generous introduction, I hope I don't disappoint given that introduction, but you know, there's at least one point that I learned that maybe I could rely on Abe for a future recommendation letter, right, given that very generous introduction. But seriously, I'm extremely humbled and privileged to be this year's Smith Lecturer. I wish I had the opportunity to meet Julian Smith, given how colorful you were describing his life was. Thank you again. I've had a very wonderful day with the discussions today, and I hope to continue tomorrow. Now it's my opportunity to reciprocate, to tell you a little bit about what we do in our labs. I thought I would tell you about molecular interactions this afternoon, and then tomorrow I'll tell you about the technology, about smart windows that we've made in our laboratory. So as a grad student, finishing up, I was inspired by these three gentlemen. So this is Hideki Shirakawa, Alan McDermott, and Alan Heeger. They were awarded the Nobel Prize in 2001 for discovering that under certain circumstances, polymers, things that are known to be electrically insulating, can be electrically conducting. Right? This was just as I was finishing my PhD in polymer physics. I was wondering what I was going to be doing next. And then I thought, oh, I could apply my polymer physics to this new class of materials called conducting polymers and organic semiconductors. And so for the last decade and a half, my group has been focusing on understanding structure and property relationships. And so we're interested in how molecular structure affects the morphology or the microstructure, which in turn give function to these materials in electronic devices. And so in the past, let me stand over here, sorry. In the past, we've looked at contributions of grain boundaries. So these are polycrystalline films, so they've got grain boundaries at the largest scale, and how grain boundaries affect charge transport. We've looked at in-plane orientation, because these are thin films, so the molecules can be oriented in plane, and how this in-plane orientation affects charge transport. We've also looked at out-of-plane orientation, because these films are thin, surface energetics matter, and so when you can control the surface energetics, you can get these molecules to either stand up or lie down, and depending on whether they stand up or lie down, that can change the charge transport character of the polycrystalline film. But today what I'd like to focus on is really down at this scale, okay, at the molecular scale, looking at crystal structure. Given a molecule, the molecule can pack very differently. In this illustration, these molecules are illustrated with these black ovals. That's their pi plane. They can pack in a two-dimensional fashion, a brickwork fashion. They can pack in a one-dimensional fashion. And as you can imagine, depending on how they pack, that influences charge transport. So I'd like to talk about how you can have influence over these different packing motifs in these semiconductors. And this phenomenon is called polymorphism, meaning that a single molecule can adopt different kinds of packing structure. Okay? This is not unique to organic semiconductors. You see this actually quite pervasively. In carbon, for example, you have different polymorphs. These polymorphs we're familiar with. You've got diamond, you've got graphite, and you've got amorphous carbon. They all have very, very different physical properties: hardness, conductivity, price or value, right? That could differ quite a bit. And if this is not your cup of tea, you can look at chocolate. Chocolate has a lot of polymorphs. The molecules in cocoa butter can pack in very different ways. And depending on how they pack, you can access different melting temperatures. And so to get the super high quality chocolate, one typically melts and then cools the chocolate down to room temperature and then heats it right to below the melting temperature of polymorph 5. That induces polymorph 5 to grow. Polymorph 5 is the one that gives you this shiny, smooth texture and this snap that everybody likes when they eat chocolate, right? Of course, accessing other polymorphs are okay, but the chocolate doesn't taste as good. So being able to select the right polymorph and getting to the right polymorph becomes very important. This is another example that's not organic semiconductor. This is Ritonavir. It's a drug. It's an antiretroviral for treating HIV. So this was introduced and approved in 1996, but then quickly withdrawn in 1998. The bioavailable version and the soluble version is this Form 1 version. It comprises of beta sheets with hydrogen bonding. Okay? And that's shown here, the crystal habits. It turns out that this, as long as there are nuclei of this Form 2 present, it slowly converts to this Form 2. Never mind that Form 2 is less dense, typically associated with less thermodynamically stable. It would slowly convert to this Form 2. And as it converts to this Form 2, it becomes less bioavailable, less soluble, less effective of a drug. Okay? So suffice to say that the possibility of polymorphism, it exists almost everywhere. The word is, if you're not looking for it, you don't see it. But if you start looking for it, you see it everywhere. Okay? But the sad thing is the conditions required to produce and prepare these are as yet unknown. And this quote is from Joel Bernstein in 2007, more than a decade ago. And I would argue that today we're still sort of in this situation where we can determine polymorphs, but we don't know how to get there. Okay? We don't know which ones are stable. We don't know how to get there. So complicating this situation is the fact that these enthalpic differences between these different polymorphs are very small. They're only a small fraction of your delta H, the melting delta H. Okay? So for all practical purposes, I'm going to refer to these polymorphs as being practically isoenergetic. And so it's really the kinetic constraints that then dictate which polymorph you access and which ones are kinetically stable. Okay? So I'm going to end with this example before I show you organic semiconductors. This is Sally Price's work. This is crystal structure prediction of a drug called tazopholone. And so these are all done computationally. And there are thousands of data points. Each of this data point is a polymorph, or is a different packing motif. The different symbols and different colors are different conformational polymorphs. So the molecule itself has a different conformation. But these are all different packing polymorphs. What I'd like you to pay attention to is the y-axis here. You can see that the y-axis spans about 20 kilojoules per mole. Not very big. And if you say you wanted to focus on the lowest energy packing polymorphs because they're more stable, you can focus on sort of the 30 lowest energy polymorphs. Okay? And there, the energy spread is even smaller. It's about 5 kilojoules per mole. So that's about 2 kTs, right? Again, this is to say that thermodynamically, the difference between these polymorphs are small. What dictates whether they're accessed or not is really the kinetic constraints. It's how you process and whether you can get over these kinetic barriers. So in terms of the energy landscape of polymorphs, I'd like to think of them as little puddles or little pits, right? I mean, they're shallow little pits on an energy landscape. So the kinds of compounds we're interested in our group look like this. These are some examples. This is copper phthalocyanine. It's more common than you think. It's used as a dye in the automobile paint industry. And I'll tell you more about these different chemistries tomorrow. But what I'd like you to notice in this slide is that they have one thing in common in all these semiconductors. That is, they have a lot of alternating carbon-carbon double single bond. And these alternating bonds basically gives us pi orbitals. And it's a pi orbital overlap that then promotes charge transfer. So implicitly, what I've just told you is that charge transport in these materials is anisotropic, right? It depends on how these molecules pack. In the direction of pi orbital overlap, you're going to get high charge transport. And in all other directions, you're going to practically get none. Okay? So this is where long-range order, this is where packing arrangement becomes important in organic semiconductors. So let me give you some examples of polymorphism in organic semiconductors. So I'll show you single crystals here, so we don't have to worry about grain boundaries for now. But then I'll come back and show you thin films. So this is rubrene. It's a quintessential organic semiconductor. You can grow macroscopic single crystals of this rubrene. And you can grow rubrene in different forms. You can grow it in its orthorhombic form or its triclinic form. And these are the crystal structures that are shown here. And then depending on which crystal structure you access, you can see that the mobility, which measures how efficient charges are transported in these materials, could be quite different. In its orthorhombic form, it's 1.6 centimeters squared per volt second. In its triclinic form, it's only 0.1 centimeters squared per volt second. Big differences, again, because here you can see, even in these crystal structures, that the extent of pi orbital overlap and electronic coupling is very different. This is this TMS-DBC compound that Gavin Collis's group actually grows in Australia. And Oana Dureshu's group at Wake Forest grows single crystals with this. Depending on whether you're growing it from vapor or from solution, you can again access two different polymorphs. One is a 1D slip sack polymorph, and the other one is a two-dimensional breakwork structure. These might look like cartoons, but they're actual single crystal structure data. And again, depending on which polymorph you access, you see big differences in mobility. This is this compound here that Wenping Hu's group makes in China. And again, you see two different crystal habits, two different distinct polymorphs. You can again make single crystal transistors with this. And again, you see big differences in charge transport, right? So subtle changes in molecular packing leads to big changes in the extent of charge transport. And this is true in thin films as well. So this work is by Ying Diao, who's now at UIUC, and this was her work while she was a postdoc in Jinan Bao's group. This is with TIPS pentacene. And so here, TIPS pentacene adopts the same two-dimensional breakwork packing, but she shears this film as the film is crystallizing. And because of this shearing, you can look at and see subtle differences in the extent of pi orbital overlap in the charge transport direction. And because of this difference, you see, again, differences in the mobility. It's the same class of packing polymorph, but slight differences in the packing motif. In the same issue of JAX, we published also a polymorphic story. Here, this is with contorted hexabenzochroanine. And here, what we showed is that depending on how you post-deposition process the amorphous film, you can access two different polymorphs. This is the crystal structure and the X-ray diffraction data that we collected here at CHESS. And what you can see is the mobility is a strong function of not only the polymorph, but also the orientation. And we can separate these two contributions by doing systematic transistor measurements. Last but not least, this is a terthiazine oligomer from Yves Geert's group in Belgium. And he's shown that depending on how fast the solvent evaporates, depending on how fast you spin coat the film, you can access a thin film polymorph. And you can see the crystal structure is different, the X-ray diffraction here. And this thin film polymorph, again, has differences in charge transport character. So we thought this is an opportunity for us. We wanted to explore polymorphism and its stability in single crystals and in thin films. And we had a set of molecules where we have subtle changes in its side chain, not the conjugated core, but the side chain. And we thought this would be a great opportunity to ask ourselves, how do these subtle chemical differences impact the stability of these polymorphs, both in single crystals and in thin films? So this is work of Jeff Purdom. You might have seen him around on campus because he came routinely for about 5 years doing a lot of X-ray work up here. He just started at Bristol-Myers Squibb. And we obtained these compounds in a collaboration with Thomas Weitz, Chao Wu at BASF, and these were actually synthesized by Thomas Gessner. So we're calling these NTCDI because these are naphthalene diimide organic semiconductors. So there are slight differences between these organic semiconductors. So let me show you what the differences are. We call NTCDI1 our reference. Okay? The conjugated core is this. It's a plate-like structure. And then these side groups are there to promote solubility. But of course, because you have side groups, these side groups occupy space. They affect the packing arrangement of these molecules internally, and I'll show you how in a little bit. NTCDI2 has one more fluoromethylene unit compared to NTCDI1. NTCDI3 is just NTCDI2, but it's hydrogenated instead of being fluorinated. And then NTCDI4 is just NTCDI1, and we've exchanged the chlorines for bromines. Very, very small changes that we're making, not to the conjugated core, but to the substituent. Okay? We can grow single crystals, and it turns out it doesn't matter whether you have 1, 2, 3, or 4. If you grow them from solution, you access this one-dimensional pi stacking motif that we call the alpha phase, and the crystal structure is shown here. These are the unit cell dimensions. Don't worry about it too much. Suffice to say that we have it. Now, if you grow it by physical vapor transport, you access this two-dimensional breakwork packing motif that we call beta phase. And you can see the crystal structure here. Okay, this is 2D because you can sort of transport charge in two directions. Here, this is 1D because you can only transport charge in one direction. So it turns out that these subtle differences in the chemistry of the substituent doesn't really matter in this case. We can access the alpha phase for all compounds. We can access the beta phase for all compounds. And when they're in their alpha phase, they look more or less the same. When they're in the beta phase, they look more or less the same. So these are quasi-equilibrium conditions that we're growing these single crystals. Okay? So it turns out under quasi-equilibrium conditions, you can access these. These subtle chemistry does not appear to matter. So this is an evaporated thin film. They're about 80 nanometers thick. This is the Afm Micrograph. And so these are X-ray diffraction patterns, again, collected here in collaboration with Arthur Wall. So the fact that you see spots tell us two things. One, it's crystalline. Two, that they're preferentially oriented. Because we have a single crystal structure, we can actually index these spots. And it turns out that if you index these spots, it tells us that all these compounds, when we evaporate them, they access the beta phase, the two-dimensional pi stacking motif. Okay? They all adopt the beta phase. In our lab, what we like to do is do this post-deposition processing to either anneal the film so that we can increase the crystallinity. And so here, this is the solvent annealing process. We take this film that is already the beta phase, and then we put it on the top of a Petri dish. We expose it to a little bit of solvent at the bottom. It's exposed to the solvent vapor. This solvent vapor plasticizes the film, and it allows for rearrangement to occur if rearrangement needed to take place. And so this is a video of the solvent vapor annealing process. And what you can see is a macroscopic change. Now, mind you, the film is already crystalline. So this is a solid-solid phase transformation that we're seeing, right? We're growing big grains here. And this is an Afm micrograph. We can take these films and we can run GIXD here again at chest. And so these are the GIXD patterns of the films. So what you'll notice is these are X-ray diffraction patterns, and they're again crystalline. But if you have a keen eye, you'll notice subtle differences. In the beta phase, the reflections, in-plane reflections, only start at about 1 inverse angstrom. Once we solvent vapor anneal in NTCDI1 and NTCDI3, we begin to see reflections at lower Q. And in fact, the outer plane reflections actually shift to higher Q. Okay? So it turns out if you index the NTCDI4 and NTCDI2, they retain their beta phase structure. But in NTCDI1 and 3, when you solvent vapor anneal it, we now convert from the beta structure to the alpha phase structure. So this is to show you the conversion. So this is the as evaporated X-ray diffraction pattern. And then for NTCDI1, and as we solvent vapor anneal it with acetone, you can see here in the outer plane reflections that shifts. Okay, so this is at about 0.35 inverse angstroms. Now we're at about 0.55 inverse angstrom is the primary reflection. You can also see big differences in the reflections at higher Q. In fact, we found that this process is actually solvent agnostic, meaning that we can access the alpha phase using acetone. We can access the alpha phase using chlorobenzene, dichloromethane, THF, and toluene. So it doesn't matter what solvent you use. It converts NTCDI1 from its beta phase to its alpha phase. What the solvent choice does is it actually affects the rate at which these grow. And in fact, it affects the rate differentially in the pi stacking direction versus the other in-plane direction. So we can get different crystal habits. Sometimes we get grains when the growth rates are comparable because the growth is isotropic. Sometimes we get needles because now the pi stacking direction grows so much faster because of solvent molecule interactions. I'm not going to talk too much about that today. What I'd like to focus on is this polymorphic transformation. So in that context, all the solvents give us the alpha phase. So X-ray is nice because we see big differences. So if we integrate in the outer plane direction, right, if we just kind of trace, do a one-dimensional trace in the outer plane direction, that's what we see. Alpha phase, the first reflection is at 0.55 inverse angstrom. And in the beta phase, the first reflection is at 0.35 inverse angstrom. It's very easy to identify whether we have the alpha phase or the beta phase. But X-ray diffraction is not very convenient. We only get beam time about 4 times a year coming up here, right? And so we have a lot of experiments we want to do. We were lucky in the sense that we see absorbance differences in UV vis, and so that we can do in-house. So in the alpha phase, its unique fingerprint is very different from the beta phase unique fingerprint. So now we know this, we can actually carry out a lot of these experiments in-house using the UV vis spectrophotometer. So what I'm going to show you is quantitative data on this transformation process when we expose the beta phase to solvent vapors. So this is the UV vis spectrum of the beta phase. That's in red. And the blue is our calculated number, calculated spectrum. And this calculated spectrum is basically a weighted function of the alpha phase data and the beta phase data. And if we track this weighted function, we can basically track how much is being converted as a function of time. So during solvent vapor annealing, this is what happens, right? You convert to the alpha phase. And so if you track the weighted function, so that's fraction alpha as a function of time, we get kinetic data of this transformation process. We can fit this kinetic data, and it turns out it fits nicely to the Avrami equation. And so we get a second order of Avrami kinetics that tells us it's a nucleation and growth process. Okay? And I'll come back to this nucleation and growth process in a little bit. Suffice to say, we can quantify this process. It turns out that now that you can get to the alpha phase, if you now thermally anneal this alpha phase, you can get back the beta phase. So these polymorphs are now reversible. You can go back and forth, back and forth. So this is data capturing the transformation from alpha back to beta. This time we're using X-ray diffraction, and we're thermally annealing the film. You can see that the reflections are identified with in red are slowly decreasing in intensity, and the white reflections are growing in intensity as a function of time during isothermal annealing. And this is shown here. This is the alpha phase data, right? And this is the beta phase that grows with time. And again, we can fit this data to the Avrami equation, and we can again get a half time. And again, it's second order, telling us it's a nucleation and growth process. So let me summarize what we see in NT-CDI1. As evaporated, we access the beta phase. We can solvent vapor anneal, and we access the alpha phase. And if we take the alpha phase and we now thermally anneal, we get back the beta phase. So it appears that these polymorphs are reversible, and we can go round and round and round and round. Now, let's come back and talk about thermodynamics versus kinetics. So Chad Risco at University of Kentucky had done some calculations for us. And so this is looking at the enthalpic contributions of the energy, so measuring the cohesive energy density. It turns out that the cohesive energy density is actually the difference is actually very small between alpha and beta phases, bringing us back to this idea that these aren't thermodynamically very different. Okay? What's different, though, is the kinetic barrier. Because we can do those kinetic measurements, we can back out an activation energy, and that activation energy is much, much bigger than the thermodynamic difference between these two polymorphs. So it appears that the constraint is on the kinetic end. So let me remind you what we've seen. So with NT-CDI1, which is the data I showed you, and it's true for NT-CDI3 as well, we access the beta phase as evaporated. And then as we solvent vapor anneal, we access the alpha phase. And then when we thermally anneal, we access the beta phase. And we can go back and forth, back and forth, and back and forth. Now, curiously, with NT-CDI2 and NT-CDI4, you access the beta phase. And then no matter what you do, you're stuck in the beta phase. We know an alpha phase exists because we can grow single crystals of the alpha phase. And yet, in thin films, we can't seem to access the alpha phase. So there are big differences in thin films that we're not seeing in single crystals. And so the question is, why is this the case? Why can't we access the alpha phase with NT-CDI2 and 4, but we can go back and forth in NT-CDI1 and 3? And remember, the chemical differences are very, very small in these systems. So we searched for a long, long time, and these are the correlations that we found. So these are the single crystal structures of NTCDI 1, 2, 3, and 4. They all have these layered structures. So these blue lines represent short contacts. You see short contacts between the pi planes. That's to be expected. We're dealing with organic semiconductors. That's the direction of pi orbital overlap. That's the direction of charge transport. Now, what's different between these two pairs is that with NTCDI2 and NTCDI4, we see these short contacts between molecules in adjacent layers. In NTCDI1 and NTCDI3, we don't see these short contacts between adjacent layers. So we hypothesize that these short contacts are what locks the structure in place, and it prevents and precludes NTCDI2 and NTCDI4 from transforming out of the beta phase into the alpha phase. Whereas in NTCDI1 and NTCDI3, we don't have these short interlayer contacts. And because we don't have these short interlayer contacts, we can transform out of this beta phase into the alpha phase. So at this point, we need a framework to quantify what these short contacts are. And so we've used a very simple parameter that we call short interlayer contacts. And that's basically the difference between the distance between the atoms on neighboring molecules minus the sum of the van der Waals radii of the same two atoms. Okay, so I'm going to say it again. It's the difference quantity between the distance of the two atoms on different molecules minus the sum of the van der Waals radii of the same two atoms. So if that number is positive, that means there's no short contact by our definition. Okay? And if that number is negative, that means there's short interlayer contacts because that distance is smaller than the sum of van der Waals radii. So by that definition, the numbers here should be negative, and the number here should be positive. Okay, and we can calculate that. And this is what our observation is, right? Beta phase is not stable for NTCDI 1 and 3 because we can transform out of it. But the beta phase is stable for NTCDI 2 and 4 because it appears that we're kinetically trapped in those two polymers. So to test this hypothesis, we decided to look at several other organic semiconductors. We decided to look at this DBTDT first because we know its crystal structure has no interlayer short contacts. And so by definition, if our hypothesis is correct, we should be able to transform in and out of its polymorph. We also tested this N1100. This is a parylene diamide. It's got a bigger core. It's got interlayer short contacts. And this, again, we can find out from looking at the crystal structure itself. And so by definition, we should be stuck in its polymorph with N1100. And in the meantime, we've tested also on numerous other systems, including TIPS pentacene, TESS pentacene, TMS DBC, et cetera, et cetera. So this is DBTDT. It's got two known phases, only one solved crystal structure. And unfortunately, the crystal structure that we access is not the solved crystal structure. And so our collaborator actually did some DFT calculations. So this is a crystal structure that's gotten from DFT calculation. And again, you can see that these are the conjugated core. And there are short contacts between the conjugated core. That's to be expected. They form a layered structure with no short contacts between the layers. And so this is the data. This is X-ray diffraction as well as UV vis absorption data. As evaporated, we access a beta phase. And then we can thermally anneal it. And that pushes us to P2. We call it P2 because we don't know the crystal structure, but we know it's a different crystal structure from the beta phase. And then if we solvent vapor anneal it, we get back to the beta phase. So this is the processing map. You can see this also by the fingerprinting in the UV vis data. As evaporated, we have a red shifted lambda max, and then we blue shift it when we thermally anneal it, and then we shift it back in the red when we solvent vapor anneal it. And we can go back and forth. So this is a series that shows that we can go back and forth, back and forth, back and forth, back and forth. And this tracks basically the lambda max. So this is consistent with our hypothesis. No short contacts, therefore we can transform in and out of these polymers. So that's here. And that's quantified by the short contact number. So it's a positive number, and it's not stable. This is N1100. That's the crystal structure. And again, here you see short contacts in the pi stacking direction, but you also see short contacts between the layers. These are X-ray diffraction data that tells us that we access an amorphous phase. And then it doesn't matter what we do, whether we solvent vapor anneal or whether we thermally anneal, we get back to the beta phase, and then we're stuck at the beta phase. Okay? It's got other polymorphs, but we don't access it. We're stuck at the beta phase. Consistent with having these short contacts present between the layers. So we can add this. It's a negative number. And this polymorph appears to be kinetically stable. So I've added other organic semiconductors. The data is the same, right? So positive, it's not stable. Negative, it's stable. So it appears that the list goes on. So then the question is, well, how robust is this? How stable is stable, right? I mean, we said beta phase is stable. Here, beta phase is not stable. How stable is stable? So we decided that we were going to test to see whether we can unlock, right, NTCDI from its beta phase through templating. So again, we conducted a very simple experiment. We put down NTCDI1. And when we put down NTCDI1, we access the beta phase. But we can solvent vapor anneal to access the alpha phase. So we have an alpha phase template. And now we're going to put down NTCDI4. Okay? Now, NTCDI4, previously, we were only able to access the beta phase. So the question is, in the presence of an alpha phase at the bottom as the substrate, can we now seed the growth of the alpha phase in NTCDI4? Okay. So that's the data. This is the reference data. NTCDI1, the beta phase, is shown here. And then when you convert NTCDI1 to the alpha phase NTCDI1, that's its fingerprint, so very different. And this is NTCDI4 in its beta phase, which we can access. Okay? Now, when you put on NTCDI4, because UV Vis we're doing through the stack, it's a transmission experiment. So it's basically through both NTCDI1 and 4. And so that data is shown in the dashed lines here. It's not so easy to deconvolute, but you can already begin to see differences here. So here, for example, in the pink dashed line, you see intensity or absorbance that you don't see in the gray, suggesting that we do have access to this alpha NTCDI4. So what we did was we collected the difference spectrum, right? So you subtract the signal from the bottom. And when you do that subtraction, you can see it clearly. So if you deposit NTCDI4 on the beta phase of NTCDI1, that data is shown in black, and that data is similar to the blue data, telling us all we have is beta NTCDI4. Now, if you take NTCDI4 and you deposit it on alpha NTCDI1, that data is shown in red, and you see extra absorbance. And that extra absorbance is associated with the alpha phase of NTCDI4. If you don't believe me, you can also look at the X-ray diffraction data, and this is more concrete, I would say, because you see a separate reflection that's associated with the alpha phase of NTCDI4. Now, I should mention that we don't get all alpha phase of NTCDI4. We get a fraction that's alpha phase. We still have a fraction that's beta. And that fraction depends on the thickness of the film, a telltale sign that this is a heteroepitaxial templating of NTCDI4. So then the question is, well, now that we have alpha and beta NTCDI4, can we now do this transformation, right? Previously, when we only had beta, we can't access the alpha. Now, in the presence of some alpha, can we access alpha with the rest of the beta? And so this is the data. This is just a reference, beta NTCDI4. This is what we start out with. We have alpha and beta NTCDI4. And as we solvent vapor anneal, true to form, the beta actually slowly converts into the alpha phase. Now, this data is significant because it's telling us that previously when we could not access alpha, it's because the barrier is a nucleation barrier. Because alpha is now present, the beta is willing to convert to alpha. Similarly, we can go the other way around. Okay? We take that film, and we now thermally anneal, and we can convert the alpha all the way to beta. So again, these are important control experiments because they tell us that the barrier that we were measuring before, the inability to convert between these different polymers, is really a nucleation barrier. Once we can overcome that nucleation barrier, the conversion's easy, so the growth part is easy. So where does that leave us? A couple of important points. These subtle changes in substituent chemistry, they don't really alter the solid-state packing, but they impact polymorphic stability. And this polymorphic stability that I'm talking about is a kinetic stability. Okay? So in the absence of these interlayer short contacts, you can use post-deposition processing to kind of convert between these polymorphs. And you can go back and forth, back and forth, back and forth. But in the presence of these short contacts, we think these short contacts actually lock the structure in place, and so you're kind of stuck. But that stuckness is because of a nucleation barrier. And so if you have a template and you seed nucleation because you're bringing that barrier down, you can now access the other polymorphs. So it's a kinetic constraint that you can overcome with heteroapitaxial template. And so what I'd like to show you is that this framework actually has strong implications beyond organic semiconductors. This is an organic semiconductor, but I'll come back to the non-organic semiconductor. So this is rubrene. And I've shown you examples of rubrene, and I've told you that rubrene has two crystal structures, the orthorhombic and the triclinic. It's interesting in this paper and many other papers that rubrene can exist in both polymorphs in thin films, and they appear to be stable. They don't interconvert. You can have it sit there forever, and it stays coexistence forever. And we believe that perhaps not coincidentally, that you see a lot of these short contacts between the layers of both the orthorhombic and the triclinic structure. And because these short contacts are present, they're just kind of there, right? It stabilizes these two polymorphs. Coming back to ritonavir, again, this is the antiretroviral drug for HIV. We don't see any short contacts in the form 1, but we see short contacts in form 2. And so once there is a nuclei for form 2, it's going to convert into form 2 because we believe that these short contacts are there. Form 2 appears to be more kinetically stable, and that's the phase that kind of sticks around. We can go to aspirin. Aspirin has 7 polymorphs. I'm showing you only 3 polymorphs here. And it turns out that no matter which polymorph you start out with, eventually at ambient conditions, you always end up in this form 1 polymorph. And under our framework, if you look for these short contacts, only form 1 has these short contacts. Okay? This is ROY. It's a pharmaceutical compound. So ROY stands for red, orange, and yellow. Not very creative. And it turns out ROY has 2 different conformers. So the molecules can be oriented and conform in 2 different, has 2 different conformations. And so ROY1 is one of the conformer. And so if you look at ROY1 has many different polymorphs. In fact, folks who study polymorphs really love this compound because it's quote unquote the most polymorphic compound around. So these are named, again, not too creatively. R for red polymorph. This is orange red plate polymorph, orange plate polymorph, orange needle polymorph. Okay? But there are many other polymorphs of ROY1. And if you look across ROY1's polymorph, all of them show these interlayer short contacts. And again, consistent with our framework, all of these polymorphs can be stable for weeks, months, years. Okay? And we believe these short contacts are stabilizing these different polymorphs. ROY2 is the second conformer. It too has different polymorphs. And again, all these polymorphs have short contacts. And we believe that's consistent with why these different polymorphs are again stable. This is guanine, a biological building block. And this, looking at this was inspired by Leo Kronik's visit to Princeton University. And so he gave a talk about guanine, and he says, well, interestingly, everybody knows the alpha phase is a thermodynamically stable phase, but nobody ever accesses the alpha phase. Everybody always accesses the beta phase. And we thought, well, this is an opportunity for us to test our framework. And if you look at the crystal structure of alpha phase, there are no short interlayer contacts. The beta phase shows tons of interlayer short contacts. And again, we believe that these interlayer short contacts is what stabilizes this beta phase. So you can add those, and again, you can see the consistency. Whenever there's a negative number, the polymorph is stable. Whenever there's a positive number, the polymorph is not stable. And so we believe this is a very simple framework, but it's an important framework because in this era of machine learning and crystal structure prediction, you can predict a lot of crystal structures. But I think there's value in knowing which crystal structure is kinetically limited and kinetically accessible. And so we believe that using our framework can help you narrow down or screen the sets of crystal structures that are predicted to see which ones we can access at sort of ambient conditions or physiological conditions. So with that, I'd like to thank the group. So Jeff Purdom, again, is a graduate student who did the work. And I'd like to take this opportunity to especially thank Detlef, who's in the audience, and Arthur Wall, who's not here, I guess. We've done a lot of these experiments in collaboration with them over the years, as well as BASF, who gave us a compound and supported a large part of this work. So thank you again. I'm happy to answer any questions. Oh.
Questions? Hugh. Thanks. Great talk. So our group did some work on tetracene, and we found that we're able to access the alpha phase when we increase the growth rate. Growth rate a parameter you consider?
Oh, so yeah, I mean, so that's, again, a different processing route, right? So you can access, so single crystals are grown at quasi-equilibrium conditions. So you can access, depending on what processing conditions you can choose, you can favor one polymorph over another polymorph. Yeah, I mean, so that's completely consistent. I think now the question is, if it sits around, whether it's stable, right? Yeah. And so we've not looked at tetracene, so I don't know the answer to that. But if you have the crystal structure, you can look, or we're happy to help you look, and to see whether there are short contacts present.
You mostly talked about kinetical aspect. Right? So is there any dynamic implication in some of your studies, for example, that interlayer contacts can be altered by some how to process in terms of spin casting or anything?
Yeah, well, I mean, that's the question, right? I mean, I think if, ideally, what would be nice is if you can unlock it when you want to unlock it, and then lock it back when you want the structure to kind of stay. And I think this heteroepitaxy templating could be a way to do that, right? So you nucleate, you lower the barrier to nucleation, you nucleate the phase. You get the phase that you can't usually get, and then once you get it, you convert everything to that phase, and then it stays there. So, I mean, I think one needs to think about those kinds of parameters and how to tune external parameters to get to, first one needs to figure out what you want and whether you can get there, and then kind of be able to design routes to kind of getting to the endpoint. But that heteroepitaxy is sort of our beginning of thinking about this. Yeah.
Very nice.
Oh, thank you.
Two maybe related questions. One is there any difference in the density between the two phases, alpha and beta, for the polymorph? And the second question that may relate is, what's the working hypothesis as to what the solvent is doing in this sort of annealing? Is it maybe going into this interlayer contacts,
Yeah.
sort of weakening them?
Yeah, yeah. So, so the first question is the density difference. There is density difference, but it's very small. Again, consistent with sort of thermodynamically, it's not very different. Practically isoenergetic.
Which one is less dense?
I forget. I think for NTCDI1 it was the alpha phase.
Yeah,
Okay, but it's very, the difference is very small. And then the second question was what again? Yeah, yeah,
There could be something.
yeah.
Okay.
What was the second question?
So in the solvent,
Oh, solvent. That's right.
because
Yeah, yeah, yeah.
it helps because it tends to weaken this interlaying contact, perhaps?
So initially we thought it was plasticization. You plasticize the film, it wants, under those conditions, it wants to go to the alpha phase, it goes to the alpha phase, right? And then we started looking, oh, how about changing the solvent concentration, or how about changing the solvent choice? And again, you always get the alpha phase, but what we see is the solvent-molecule interactions can change the relative growth rates, right? So the pi stacking direction, growth rate is highly dependent on which solvent you use. When you use an aromatic solvent, it interacts with the conjugated core. It retards that growth direction. And so what happens is you get these isotropic growth, and so you get sort of plates. Now, if you use a solvent that interacts with the substituents instead of the conjugated core, pi stacking is actually pretty fast. We see evidence of H aggregation in solution, which we believe is a precursor to the alpha phase. And now pi stacking grows pretty fast. And in the solid state, we get needles instead of plates. So it changes the crystal habit, but it doesn't change the fact that we access the alpha phase, which was deceiving, right? Because, I mean, typically you look at the crystal habit, it's a different crystal habit, you go, it's a different polymorph. And that's how we started. And it turns out the polymorph's the same, and that was from the X-ray diffraction data. The crystal habit's different. Because, again, you're so far away from thermodynamic, it's the kinetics that matter now, and so these interactions matter. And so when you can grow fast, it grows fast. When there are interactions that blocks it from growing fast, it grows slowly, and you get these isotropic growth.
Any questions out there?
There's one there.
Oh, there's one.
Yeah, to build off of Fernando's question, all the solvents you chose were either aprotic or non-polar. Did you try protic solvents by chance?
I don't remember. We tried a bunch of solvents. And so there are 3 general classes of solvents. Sometimes we see excimer formation. And then the aromatic ones that interact with the core, we see sort of these, the hindrance of pi stacking. And then in another class of solvents, we see sort of these H aggregation. And in fact, the telltale sign is if you look at the solution, sometimes you see pink color, sometimes you see yellow color. And so that's when we started to explore, the emission and the fluorescence of the solution. And that's how we now trace back to what happens in solution affects what happens in the solid state. Yeah.
So is there a way to connect or relate the chemical information to the ability of these things to form these short contacts? So for example, NCCI1
Yeah.
versus NCCI4, the difference is just a chlorine versus
Yeah.
a bromine.
Yeah.
If you go to an iodine,
Yeah.
do you predict whether or not you'll form these short
No,
contacts?
well-
How do you sort of get at that information?
Yeah, so we're hoping to get there. The answer is not yet. I mean, we've got a number of collaborations with Paulette to kind of think back, using sort of computational methods to kind of guide what we're seeing. But we're not there yet. So bromine actually has an effect, right? I mean, because it allows either the core to come closer together or further apart. And so if you want to think about aspect ratio of the core relative to the side chain, that could change, that size, the dimension aspect ratio changes. So that could have an effect. And so that's where we sort of started. We thought, oh, maybe it's the relative size
So
of the
the
core
size
to
of
the side chain.
polarizability, do you think?
Yeah. So we don't have a good sense yet. So we need to start with a crystal structure. If you give me a chemical compound without a crystal structure, we don't yet have intuition on whether you have short contacts or not. But if you give me the crystal structure, I'd be able to tell you. Yeah.
Then a related note, right, Lynn? So does this framework ever not work? And can you learn something from that about the types of interactions where it fits?
So I'm glad that it hasn't. We've not come to that situation. Again, because it's a framework, right? But I'll tell you about BMA IFD. So this is an organic semiconductor. So I was giving a talk in China, and a professor in the audience, Zhang Hao Li, raised his hand. He's like, well, I've got this organic semiconductor. We don't think it has short contacts. But it's not we can't transform it. And I go, really? If it doesn't have short contacts, why can't you transform it? And so I was kind of bummed, and I go, well, why don't you share your crystal structure with us and let us take a look at it? So we looked at his crystal structure. True enough, it doesn't have any short contacts. So we went back to his students, and we insisted that they tried a bigger phase space. By heating longer and higher temperature, so they were able to transform back and forth. And so we're writing a paper now. So a lot of these examples came from things like that, right? Because then people are like, well, have you tried this? It probably won't work. And so we've tried it, and it seems to work. Yeah.
John, so you seem to be making your arguments based on the enthalpy, but
No.
Well,
To the contrary.
I mean,
But
that's the y-axis you had for theory, sorry, Paul, that were all enthalpy. And that's the first question. Okay, so you already answered that one.
wait, what was the question?
Well, should the entropy matter?
Entropy.
Yeah, because the Gibbs free energy should run the show at constant pressure.
Well, I mean, I guess my point is the Gibbs free energy is not running this show. So, I mean, I showed the y-axis, and I showed how small the differences in energy levels are. It's really the barrier that matters. Sure. And so it's a kinetic problem, not a thermodynamic problem.
Barrier too, right?
To me, Gibbs free is the delta between the two states, right?
Well, delta H minus T delta S, the entropy comes in too.
That's between the two layers.
That's if you believe it's a thermodynamic problem, right? And I'm saying it's a kinetic issue. So the thermodynamically, the energies, delta G, delta H, okay, so we didn't calculate delta delta S, but we're saying delta H is a proxy of delta G, and so the difference is small. Yeah.
So the second question was you're making arguments based on their crystal structure,
Correct.
but these are polycrystalline films, and so right, and so does when the solvent comes in, does it go through the bulk or does it diffuse across the grain boundary? That is, does it matter that you have the grain boundary?
Sure, sure.
How crucial are those?
So there are two questions that are sort of buried in that one question. Just because they're polycrystalline doesn't mean the crystal structure doesn't work, right? The crystal structure is fundamentally at a different length scale. It's a smaller length scale. So polycrystalline just means you have the same crystal structure, but maybe they're oriented a little differently in each grain. So that's that. And then now what happens to the solvent? Does it come in through the grain boundaries? Does grain boundary play a role? I can guarantee you grain boundaries play a role. Now I can argue that it slows things down or it hastens things up. I can have arguments both ways. We haven't done the experiment. The one single data point we have is if you do single crystal, if you do a transformation with single crystal, it happens much, much slower. But that's one specific example. I mean, I can see arguments going both ways, that grain boundaries can facilitate this transformation because it can nucleate this transformation. I can also see it the other way around, where grain boundaries retard this transformation because once you nucleate, I mean, you can only sort of, go so far. That's right. So we're headed in that direction. We can control the grain size now, so we can kind of systematically do these measurements, and we can access single crystals, so we can do these measurements as well. Single crystals are a little different because they don't have the substrate. Here we have a substrate. If you notice, the X-ray diffraction patterns are all preferentially oriented out of plane. Now, whether the preferential orientation matters is something else that we need to consider. So going from single crystal to polycrystalline film with different sizes of grains is important, and that's sort of where we're going next.
I think we better hold questions, but before we thank our speaker, come back tomorrow for an exciting set of applications with related materials.
Totally different talk.
So please join me in thanking Professor Liu.
Thank you.